door number 2 are $1,001 bills.
What?
Do you want what's behind door number 1 or door number 2?
Number 2.
The show is going to lose a lot of money. So, which one has the higher average per bill? Door number 1 or door number 2?
1.
Door number 1 does. Has one $100 bill.
Yeah.
Which one has the greater total value? The second one, right? Let me turn this into something that might not be quite as obvious. So, what has the greater average translational kinetic energy per particle? The molecules in a cup of hot water or the molecules of water in my swimming pool? I'm cheap, I would never turn on the heater in my pool.
Can you repeat your question again?
What has a higher average translational kinetic energy per particle? The molecules of water in a cup of hot water or the molecules of water in my swimming pool?
Molecules from a cup of water.
The molecules in the cup of hot water, the average translational kinetic energy is the temperature, right? Average translational kinetic energy per particle, right? And so the average translational kinetic energy per particle of the molecules in the cup of hot water definitionally is greater than the average translational kinetic energy per particle of water in the swimming pool. Yeah?
Right.
Higher translational kinetic.
Higher temperature means higher average translational kinetic energy per particle. Yay?
Yep.
What has more total energy? The cup of hot water or the water in my swimming pool? I'm a public school teacher, and yet, you know, the pool is still big enough that yeah, the molecules in the swimming pool, just by dint of having so many molecules, even though they have lesser energy per molecule, still has a greater total energy. Does that work? Okay.
So is that higher temperature, the greater whatever kinetic energy you mentioned?
Average translational kinetic energy per particle. So more temperature means that the average translational kinetic energy per particle is also higher. Yay? Okay. What I'm going to tell you is this value, our minus 273.15 degrees Celsius, is also going to be what we're going to call absolute 0 Kelvin. And at this point, well, the average translational kinetic energy per particle of that sample would be 0 if we could get to absolute 0. Does that make sense? We can get very, very, very close. Yay? That's our, so the other thing is that a long time ago we decided we liked the size of 1 degree Celsius. And so, I don't know, let me add yet one more, our Kelvin scale. We're going to say roughly 273 Kelvin is the temperature at which water freezes, and roughly 373 Kelvin is the temperature at which water boils. So far, so good. So note that the size of 1 degree Celsius and the temperature change measured by 1 Kelvin are equivalent. But the nice thing about the Kelvin scale is 0 really means 0, right? There's no negative values on the Kelvin scale, whereas if you've ever spent a winter in New England, there are days that are, or at least feel like, negative values on the Celsius scale, depending on where you are, maybe even on the Fahrenheit scale.
Professor, have they ever made materials at 0 Kelvin, 0 Pascal?
No,
That hasn't been possible.
no. Although my, so
Is it possible?
my friends don't do low temperature physics, but even, you know, even in the work that we did, like, you know, we would work on the 1 Kelvin scale, even like the half Kelvin scale. I mean, and we don't do low temperature physics, right? Folks who really do low temperature physics can get down to like the micro Kelvin. So,
That's pretty cool.
but, you know, actually reaching 0 Kelvin, we're gonna have some thermodynamic issues with that, and that's something that we can talk about when we talk about the laws of thermodynamics. Better, go for it.
Yeah, if Celsius uses water, the freezing point of water and a boiling point for water, what does Kelvin and Fahrenheit uses?
We're still using the same thing. We've just said that Fahrenheit, water freezes at 32, it boils at 212. There's 180 degrees. There's something cute about that in between. So break the temperature at which water freezes and the temperature at which water boils into 180 steps. That's the size of 1 degree Fahrenheit. Kelvin really is referencing its 0 to this point where these lines would intersect. But it's still tethered to the Celsius scale, right? We wanted to keep 100 degrees or 100 spaces, tick marks, between where water freezes and where water boils. And so the Kelvin scale just shifts the Celsius scale back until you couldn't get to a negative value. Other questions? All right, so I think we're okay with that. My little nephew,
That's how small he is, huh?
well, no, now my nephew's like that tall, which is funny because my brothers are my height and
Impressed.
my sisters-in-law are shorter than us, but yeah, my little nephew. Let me say this, where's the camera? My brothers are horrible people. And if you ever see them, please kick them in the shins for me.
Public service.
They were horrible to me when I was young, and so part of my my plan that I started when I was very young also was because they're 10 and 12 years older than me. When they had children, I was in college. I offered to babysit as much as I could, and I did everything in my power to turn those kids against. So,
There comes a plan.
but when I started teaching, my nephew would come and sit in on classes. But then I used to talk to him, "Hey, little nephew," and so then he stopped. But I'd push him on the swings, and he loved it. Like it was his favorite thing. He'd squeal. But he also he used to run around with those little sparklers on the 4th of July. So the sparks coming off of those on the order of about 4,000 or 5,000 Kelvin. Was it poor parenting that my brothers let him run around with those? No, it really wasn't. Lots of other poor parenting decisions, like letting me babysit. But why wasn't I worried about those sparks hitting my nephew?
Because by the time they reached his skin, they weren't going to be that temperature.
That's probably true. Why not?
Because of all the molecules in between his skin and the actual spark having to reach his skin.
What if one of those sparks really did land directly on his skin, like from a very short distance?
It would probably just burn a little hair, if anything.
It wasn't a concern because those sparks are so small,
The
right?
size of them as well.
That explain it to me in terms of temperature being a measure of the average translational kinetic energy per particle.
Per particle, since the particles of the sparks are so small compared to the particles that it has to travel to get to the skin, by the time it gets to the skin, the transference of energy is going to be reduced to the point where it's not going to hurt them.
So let me reframe this slightly, but yeah, that's it. The average translational kinetic energy of those particles was really high, right? But it's made of so few particles that it's effectively there's not much
Dampened.
total energy there, right? It's the difference of one $100 bill or 1,000 $1 bills, right? Yes, the average value was very high, but the number of particles was low enough that even a high average value times so few particles just wasn't enough total energy there to do any real damage. Does that make sense?
Dampening.
All right, so then we are going to start to talk about thermal energy as being microscopic kinetic energy and microscopic potential energy. What time is it actually?
3:41.
3:41. Minutes are okay.
So it's 3:41 and this actually ends at 3:55, right?
Yes.
Okay, so stop me at some point.
Alright.
So let's introduce this notion of heat. That's not how you spell quantum. So I posed this to you a moment ago. What's going to happen when we bring into thermal contact two objects at different temperature? Well, energy is transferred from the warmer object to the cooler object. In that case, imagine that I took a penny and put it in the oven and heated it up to, I don't know, 400 degrees Fahrenheit, and then I threw it in my cold swimming pool. Which one, again, has more total energy? The swimming pool does, right? But which one has the higher average translational kinetic energy per particle? The hot penny does, right? So if you take a hot penny and drop it into a cold swimming pool, energy transfers from the one that has the higher temperature to the one that has the lower temperature. And so even though the pool has more total energy, the energy flows from the one that has the higher average translational kinetic energy per particle, the higher temperature, to the lower. So energy will flow from the penny into the pool, not from the pool into the penny, at least not on the grand scheme of things. Yay? Okay, so this transfer of energy will continue until we achieve thermal equilibrium, until the two objects share a common temperature, until they have a common average translational kinetic energy per particle. And so that transferred energy, the transfer of energy caused by a temperature difference, that transfer of energy caused by a temperature difference, that's what we mean by heat. So this is energy in transit. So this gives rise to calorimetry. So calorimetry is going to help us explore how much energy it takes to change the temperature of a unit amount of substance by a unit increment of temperature. And so let's see, how do we want to do that? We'll come back and do this in a more calculus sense in the not too distant future, but let's switch forward.
Professor,
Sir.
could you go back? I didn't quite finish
Let me swap boards. And here's where it all falls apart. Let it be known that I knew that this was not a good idea before I did this.
Nope. You're good.
Third time's the charm? No? Are you done writing it down, Chad?
Yep.
Okay, well then we'll.
What's the shot?
I think that what we've learned is that the batteries don't work in that remote, so. Okay, so. Let's look at an example in this family. Is this still pointed at me? Okay. Our goal here is to find the equilibrium temperature. So I'll say this in case my handwriting is too small for the video. 10 copper pennies, roughly 30 grams, in boiling water, are then rapidly dropped into 100 grams of water, initially at 20 degrees Celsius. The specific heat capacity of copper is 0.093 calories per gram degree Celsius. The specific heat capacity of water is about 1 calorie per gram degree Celsius, and we want to find the equilibrium temperature that they settle at. And so, so can you help me block diagram this? So we have 100 grams water, 20 degrees Celsius, and then we have 30 grams at, what's the temperature initially for the 100 Celsius? And so, which way is energy going to flow here?
From 100 to the water.
From the copper to the water, yeah?
Yeah.
Okay, so if you believe in energy conservation and we're ignoring any losses to the whatever's holding the water, and we do this rapidly enough that we don't have to worry about the copper giving away energy to anything else either as heat, then whatever energy is lost by the copper needs to be gained by the water, yeah?
Yes.
And so we can say that that's a fair statement.
Yes.
Is it negative because it's losing energy?
Yeah. If I was really doing a conservation of energy statement, I might put these both on the same side and say that the total change in energy, right? So delta E copper plus delta E water is 0. I can bring this to this side, and then I can say in this case it's the transfer, right? So minus the energy transferred out of the copper needs to be the energy that's transferred not into the copper, into the water. And so here, there's one more piece of unspoken information. So I could write this as minus M copper, C copper, T final copper minus T initial copper, which was 100 degrees Celsius, needs to equal M water, C water, T final water, minus the original temperature was 20 degrees Celsius. What's the last bit of unspoken information here?
Final temperature.
What about the final temperature?
We don't know what it is.
True, but there's something still in this that is hiding there that I haven't mentioned.
The mass of water?
I gave you the mass of the water,
Oh, yeah.
The C.
Brian.
Oh, I was just gonna say, well, technically the final, the temperature of the water is gonna be the same as the copper.
Yep. So this is done transferring energy when they achieve a common temperature. And so I don't actually need to subscript this
Yes.
copper and water. They're going to get to the same final temperature.
40 degree, right?
No.
What about
We can do this problem in 2 minutes.
Do it.
Because it is one equation written in terms of one unknown, right? And so you guys have calculators. So I suspect that it will be much closer to the temperature of the water initially,
Yeah,
because the specific heat capacity is more than 10 times smaller. And there's a bigger mass of water. So. I'm out of time. I will leave this to you to sort out, but I don't promise, I think that this is about 22.1 degrees Celsius.
Don't take your word for it.
Don't take my word for it.
Oh, well.
I'm out of time. As always, you guys are awesome. Have wonderful days. Thank you for stopping by. Don't be strangers. Enjoy your days, but not so much that we don't see you next time, which is Wednesday in person. Tomorrow I'll try and host our we'll see how it goes.